One of the most important mathematical aspects of Schrödinger's equation is that it is linear. Now, we've talked a little bit about this concept before, but we can see explicitly here that Schrödinger's equation is linear. And in particular, one thing that we notice is that the wave function psi only appears in first order. That is, there's no psi squared terms or psi cubed terms or any other higher order terms anywhere in this equation. And that has the simple consequence, almost a trivial one it seems, that if psi is a solution, so also is a times psi, regardless of what constant a is. And as I said, this almost seems so trivial here. If I were to replace psi by a times psi on both sides, it obviously still solves this equation. If, however, we had had terms of psi squared or psi cubed or something else, say on the left-hand side here somewhere, this would not be true. If I replaced psi by a times psi, it would not still be a solution of this equation. And of course we can see why a times psi is still a solution. It just corresponds to multiplying both sides of this equation by the same constant, and hence the equation is still solved. So as I said, this almost seems trivial, but it's actually not trivial. It's a very important point.
This linearity of equations in quantum mechanics is very general and important. Quantum mechanical equations are linear in the quantum mechanical amplitude for which the equation is being solved. Here, the wave function phi. In classical systems, we often use linear equations as a first approximation to nonlinear behavior. For example, a pendulum actually oscillates at slightly different frequencies for larger amplitudes. But the equation is not exactly linear in that amplitude, but it's an approximation and we can treat it as a linear equation for small amplitudes. In quantum mechanics, though, this linearity of the equations with respect to the quantum mechanical amplitude is not an approximation of any kind. It's apparently an absolute property of such equations in quantum mechanics. This linearity allows the full use of linear algebra for the mathematics of quantum mechanics. And we will be progressively developing this mathematics as we work through some example problems here.
One of the consequences of this linearity of Schrödinger's equation is that we can normalize the wave function. So let's look at this concept of normalization and how we do it. As we've already said, Born postulated that probabilities, such as the probability of finding a particle near some point r, would be proportional to the modulus squared of the wave function. So that was his postulate, and this postulate runs through all of quantum mechanics, by the way. So specifically, we could define P of r here as what we might call a probability density. So for some very small, typically we like to say infinitesimal volume, d cubed r, round about this position r, we would be saying that the probability of finding the particle in that volume is P of r d cubed r. And in that sense, P of r here we're calling a probability density. So the sum of all such probabilities should of course be 1. So that means that if we were to integrate the probability density over all space, then we should get 1. The idea being that the particle has to be somewhere. So the question is, can we choose psi of r in such a way that we can use the modulus squared, psi of r modulus squared, as the probability density, not just something that's proportional to the probability density? Well, when we did our original solution of the equation, unless we'd been very lucky, our solution to that equation would not have given us a psi of r in precisely the form such that the integral of psi squared modulus squared r d cubed r was equal to 1. That would have been unlikely just if we had done some solution. So generally this integral of the modulus squared of psi of r would give some other real positive number. And for the moment, and for a reason that will become obvious soon, we'll write that number as 1 over the modulus of a squared, a little a, which is going to be some number, possibly a complex number. That is, what we're saying is, let's suppose we've done a solution here, and we've got some solution to our Schrödinger equation, psi of r. We take the modulus of that squared, we integrate it over all space, and we get some number, and it's going to be a positive real number because all of these are positive numbers, and also real numbers because this is a modulus squared. And we're just going to call that positive real number 1 over the modulus of a all squared. Now, we know that if psi of r is a solution of Schrödinger's equation, so also is a times psi of r. This is this consequence of the linearity of Schrödinger's equation. So if we use the solution psi n here, I'm going to put a subscript n on it, which is a times psi, instead of the solution psi, then the integral of the modulus squared of psi n of r d cubed r is 1. And then we can use this quantity, modulus squared of psi n of r, as the probability density. Psi n of r would then be called a normalized wave function. So, to summarize normalization, we take the solution psi that we've just obtained from some solution we've done of Schrödinger's wave equation. We integrate the modulus of psi squared of r to get some number that we call 1 over mod of a all squared, but it's just a number that we've got from that integral. That gives us our a, or at least the magnitude of it, and we can then choose a new wave function, our normalized wave function, which is a times psi, and then when we take the integral of the modulus squared of that over all the volume, we are indeed going to get 1. And then we can use this modulus squared of psi n of r as a probability density. Now, we need to make a couple of technical notes on normalization. The first one is that, as I mentioned, we only really are setting here the magnitude of this constant a. We're not setting its phase by this process we've just discussed. And in fact, we're free to choose any phase we like for a. Indeed, in our original solution psi of Schrödinger's equation, we could have multiplied that by any e to the I theta that we liked. That's just another number by which we can multiply the solution of psi in this linear equation, and that will still be a solution. A second and more tricky technical note is that if we think of space as infinite, then functions like sine kx or cos kz or e to the I k dot r cannot be normalized in the way we've just been discussing. The problem is that you don't get a finite result. The integral just keeps on going and it never converges to anything. And the mathematical technical term for this is to say that their squared modulus is not Lebesgue integrable, or they are not what are called L2 functions. Now, this terminology doesn't really concern us much here, but I want to emphasize that this difficulty is a mathematical one. It's not a physical one. It's a consequence of us having over-idealized the mathematics. We love to work with functions like these. They're very easy to work with, and they're solutions of other idealized equations. But this is a price that we are paying for using these very simple functions. We end up not being able to normalize them here. In any real physical problem, we're not actually going to run into this difficulty of normalizing wave functions, but when we set up somewhat idealized mathematical forms, we can run into technical difficulties. Now, there are a few workarounds for this particular mathematical difficulty. One of them is, well, let's only work with finite volumes in actual problems we're going to solve. And this is the most common approach to solving this particular difficulty, and we will do that quite often. There is also another trick called normalization to a delta function, and basically what we're doing there is introducing another infinity to compensate for the problems we introduced by putting in the first one. This can be done, And we could go through the mathematics of that, but we won't do that here. We're going to try to avoid having to invoke this particular technique.